All right, so what happens when something is inconclusive in terms of my two criteria that we have for direct comparison? Um, if our comparison is inconclusive, then we're going to use the limit comparison test. Basically, we're still going to choose a series to compare it with, and then we are going to find the limit of the series. So we have a sub n over b sub n is equal to c, where c is going to be some number. Now, in this case, it doesn't really matter whether a sub n or b sub n, which one's bigger, which one's smaller. So in this case, you could do b sub n over a sub n. It doesn't really matter in terms of that. Now, if the limit is 0 whenever you divide it out, then the series will converge if the other series converge. And then same thing for the third bullet point. If it's infinity, then a sub n would diverge if b sub n diverges in terms of the series. All right. So we're going to look at number 10 here, and we're going to start off very easy in terms of looking at the comparison here. So here's why we can't use direct comparison for number 10. If I were to compare this with 1 over 2 to the n, we are going to see that 1 over 2 to the n is less than 1 over 2 to the n minus 1. But once again, we don't have a way for us to look at that in terms of the convergent series on the left side. So that's why you have to use the limit comparison test. So our second step is going to be a little bit different here, because what we're going to do here is take the limits as n approaches infinity. And what we're going to do here is just do 1 over 2 and 2 to the n minus 1. Divide this by 1 over 2 to the n. Now, I'm not a big fan of that notation, because what you could do is just take the reciprocal and multiply it. It's neater, and it doesn't waste too much space in terms of my layouts here. And then you're just looking at this case, relative growth rates and exponents. In this case, the limit is going to be 1. Because 1 is between 0 and infinity, then we can look at, or we could write our little statement now. So now we could say that since, or because my comparison converges by geometric series, r is 1/2 is less than 1. Always make sure that you justify why you know that the series converges or diverges. Our original series converges. But this time it's not going to be limit. It's not going to be direct comparison test. It's going to be because of the limit comparison test. Limit comparison test. All right. Now, looking at something like number 11 here, where we don't really know what the direct comparison test will tell us, we know that whenever we are choosing a series to compare, which I didn't tell you guys in the video, we probably want to compare it in terms of the exponents. So whenever we are looking at the comparison for number 11 here, we're going to compare this with 3 to the n over n squared, which is 3 to the n. Okay, now likewise, I don't know what or how to compare this using direct comparison with 3 over n and 3n minus 1 and n squared plus 1. So what I'm going to do is, once again, use the limit comparison test. So we're going to have the limit as n approaches infinity. Likewise, like I said, it doesn't really matter which one's first. So here I did the original series first, but I could do the comparison first. It doesn't matter. So we have 3 over n and then n squared plus 1 over 3n minus 1. And then if I think about this, this is n squared, this is also n squared, this has a coefficient of 3, this is also a coefficient of 3, so this is going to be 1. Okay, so because we know that the limit is between 0 and infinity, aka it's some number that's not 0, and it's some number that's not infinity, then we could just verify that the series that we compared it with, in this case 3 over n, is a divergent harmonic series. Therefore, my original series also diverges by a limit comparison test. Now, like I said, the limit comparison test, I like it better because you don't necessarily need to think about what you're comparing it with and seeing which one's smaller and which one's bigger. So what I'm going to do is actually go back to number, let's say, 5 here, and think about, actually, no, let's not do that. Let's actually do 2 again. I'm going to do 2. We're still going to do the same comparison, except this time for number 2 from the last video, we are going to do it using the limit comparison test. So we have the limit as n approaches infinity of 1 over the cube root of n squared minus 2 times n to the 2/3 over 1. Notice how that limit is 1. And then because we know that this series right here, my comparison diverges by p series, tell me why, then we know that this right here, my original series, diverges by a limit comparison. So notice how, once again, if you can't compare to save your life, then probably use limit comparison. Like something like number 13 here, she looks like a hot mess right here. Okay, so what we're going to compare this with is, let's see, the square root of n and then the square root of 4n squared. I'll probably need to simplify this first. So let's see, the square root of n is n to the 1/2. 2n. So then if I were to do my final comparison, this is going to be compared with 1 over 2 to the n 1/2 right here. And we already know that for a fact that this is always going to be a divergent p-series because 1/2 is less than 1. So what we have to do here is just verify that works by taking my limit right here. Once again, if I think about my relative growth rates and my exponents, 1/2 right here and 1/2 right here becomes 1. The square root of n squared also becomes 1. The coefficient is 2. This coefficient is also 2. So this limit here is 1. And then because we know that my comparison series, 1 over 2 n to the 1/2, is a divergent p-series, Then we know that my original series diverges by limit comparison. All right, so that's it in terms of this video, and I think the next one is going to be on alternating series tests, which I've already done a video on.